Okay, so this is kind of our second presentation on applications of differentiation. I think you remember we looked at how we can get equations of tangent line, normal line. That was the first presentation. So today we're looking at what we call curve sketching. Curve sketching. In other words, here we're going to look at how we can use differentiation to sketch a curve of a function, using the facts about the derivative of the function and so on. Now, let's start this way. Let's say we're given that kind of a function. If you look at the roots, the zeros of this function, they are 1, 2, 3, 4, 5. So we can maybe say this is a kind of a 50-degree polynomial. But this was just thrown freehand without any kind of an expression for f of x. And that is not important for now. Now, remember what we said the interpretation of the derivative was. We said a derivative geometrically, it represents the gradient of the tangent line at a point on the curve of function. Now, thinking about that, so when we plot a curve of a function, it's very important to think of what we call critical points. In this case, critical points, I'll be referring to points like the zeros of a function. Let's mark them there. The zeros of function. You can't just stand up and sketch a function without first of all making the sense of its intercepts with the x-axis, which we call the zeros. So that is very important. The zeros of the function. And then the other points which are very, very important are the turning points. If a function has got zeros, somehow it crosses the x-axis twice. Somewhere it must have a turning point. I think that is clear, isn't it? So for that, you must understand that at a turning point, the tangent line is going to be horizontal. Then that's what we can represent there as something like this, somewhere there, where the graph cuts where the line, the tangent, the horizontal line cuts the, so we know there's a turning point. But when we are at that point, we must understand that there, the derivative of the function at that point exactly, the derivative there, dy dx would be equals to 0. So then sometimes, yes, a function can have more than one turning point. So then, looking at this curve, we can see we've got another turning point somewhere there. Same thing is going to happen, the derivative is going to equal to 0. What is the derivative? The gradient of the tangent line. So this line will be something like y is equal to 0x plus c. C, the point where it cuts the y-axis, the y-intercept. So again, we expect there the derivative to be 0. Do you agree? Yes. The rest now I think you can see without a lot of explanation, all that makes sense. Now having especially like having the derivatives 0 somewhere, I mean if you talk of the 0, you can think of the left hand side of 0 and the right hand side of 0. All together. So we then need to check what is the behavior of the function on the both sides of the point where the derivative is 0. Then it's when maybe we can talk of something like this. If we look at a point somewhere there, you see that tangent line is going that way, which means the gradient gradient for that line, which in this case m, must be greater than 0. Actually, where are we going to get this m from? Any point which lies between this point somewhere there, you are going to evaluate the derivative and then make sure that the derivative is greater than 0. If it's greater than 0, then you know the function is increasing, is growing. So maybe let's just do this for a while here. It's important for things to look beautiful. So we know that we're talking about this point here, isn't it? So that is the gradient, the gradient for that line. Are we together, guys? So then, also, on the other side, we can also evaluate the derivative, and you see somewhere there, I think this is the wrong line, this is right line, this one. Somewhere there, for that line, the derivative is negative. All those are things you must monitor when you are sketching a curve, because it's telling me now that between these 2 points, which are zeros, there's a turning point. How is function going to behave this side of the turning point? How is it going to behave on that side of the turning point? All those effects which you must make sense of before you can start sketching a curve. Okay, so I think also we have got some similar situation somewhere there. And the other situations we've got the function increasing. I think you've got that there, and they also got this other side there, the function increasing. So the lines there of giving Pascal, the most important thing, this is a picture, but you must put words into the picture, you must put some sense, and you must be able to talk what are these lines representing. Are we together? Then one other important thing which we need to determine also is what we call concavity. 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 I think there's a Y there. So concavity, I can remind you of your physics lesson, or general science lesson, whatever you want to call it. This is a concave lens, but this one is a convex lens. Convex and a concave. If you throw these things horizontally, just make them lie horizontally, you will see something which looks like more or less like this, which is convex. And in some way, you will see something which shapes more like this, which is this one. If it's lying horizontally, the top will be shaped more or less like this one, concave. Is that? So water will rest on a concave, but it will be thrown away over a convex portion, isn't it? So that also you need to know, where is the curve concave, where is the curve convex. But somewhere between these two, a curve cannot just be convex and suddenly be concave without a kind of a point where it's going to turn around, is it? So if you look at that, somewhere here, I don't like that. There's something which must be crazy somewhere. Okay? Somewhere between those 2 points there, now the turning point and this 0 here, there's somewhere where the curve tilts. All together and change from convex to concave. Then that takes us to the second derivative of the function. All together. Let's take us to second derivative of function. Then what's going to happen there? What's normally going to happen is where is concave That's the derivative, second derivative with respect to x. And you write there for the second time. There, this value will be less than 0. And on the other side, this value will be greater than 0. Are we together? I think we've got a summary. There are still some more things you're going to look at as we go on, but these are, I think these are the core essential things which you must not never ignore. Like also at a turning point here, there are two ways you can check whether the turning point is a point like this one, and like this one. We normally call them local minimum. Local minimum. Local minimum. Local, like local minimum. These two. And the other two there, they will be also called local maximum. There's another term which is used by your book. I can't remember what they say there, but it's not very important. It's just saying that this point here, in this locality here, around, actually in this region around this point, is the lowest point. But it's not the lowest point for the function. The lowest point for the function, actually, we don't know. This function decreases throughout this way. We don't know. That's what we call the global minimum. That was the minimum for. That will be the minimum value for the function as a whole. And then increasing this way, we'll maybe moving towards the global maximum. But we're not worried about that one because this will happen maybe at infinity, and we're never going to get to infinity at least this semester. Okay, all together. So that's fine. Okay, now let's move on to a particular example now and try to do all these things. Are we there? Okay. There is a function. There is a scale drawn there. I hope it's going to help us. I drew this to a rough scale, but it's not really very precise, but I think it's going to demonstrate the point. Copy the function. I think that's important. Because all those calculations of derivatives, I don't want we work to do that on the where I'm going to draw the graph. I want to do it on a rough piece of paper somewhere on the side where it's not going to interfere with the graph. Is that all right? So do you have the expression? Do you have the expression? Okay. Now if you've got the expression, let's come to the next page here. What is the expression? Y is equal to 2x cubed plus 3x squared plus minus 12x. Okay, minus 12x. I prefer that for organization, let's start with the intercepts. Maybe I didn't mention this before. There's the zeros that intercept on the y-axis, and we can also get the intercept on the zeros that intercept on the x-axis, and another intercept we expect it on the y-axis, and the x-axis and the y-axis are special lines. We know that if it's an intercept on the y-axis, x must be 0. Then we compute what so let's start by saying the intercepts. That is our 0 step here, initial step. Intercepts. Remember I said always when I'm using 0, I'm marking the initial step. That is the beginning of the experiment. It's not the beginning of time. So intercepts, let's say on y. When I'm saying on y, I mean on y-axis. Oh, I'm writing a new word there. On y-axis, set our x equal to 0. If you set your x equal to 0, then you will see that your y is also 0, isn't it? So y equal to 0. Don't need even to have a start calculator. You want to use a calculator for that? I hope not. So now you know that this function passes through the origin, and that origin coordinates 0, 0. Then they say on x-axis, on our axis, our y should be 0. So if we say y is 0, we're setting up an equation which says 2x cubed plus what? 3x squared minus 12x equals to 0. But we've already got another factor which is x, isn't it? So we are left, we can do this way. 2x squared plus 3x minus 12 equals to 0. Already x is 0, so we've got that one. It's not a problem. So the other one now we can say 2x squared plus 3x minus 12 equals to 0. Can we factorize that? Can you factorize that? If you cannot factorize, you can use the formula. Check if you can factorize that. If you can factorize, it should look like something like 2x and the x somewhere there. Can you factorize? Huh? I didn't factorize. I didn't even worry about factorizing myself. But I know about students I taught to factorize. Big man, why are you just sitting doing nothing? You must be pushing the pen. Are you waiting for Jerusalem? Guys, push the pen and factorize. You can't just wait as if you're waiting for Jerusalem to deliver manna from heaven. It's not right. You have the factors? No factors. Then you can use your what? Formula quickly, please. Quickly use your formula. I think if you use your formula, it should be like that. Minus b, which is minus 3, plus minus 3 squared. Yes, 3 squared plus 4 times 2 times 12. Is that all right? Yeah, 4ac. Minus 4xc, according to the formula, but plus there. What are we getting? What are the values we're getting there? X is equals to 1, 8 or negative 3, 3, 3. Negative. Okay. So I think what you can do now, we can go to the graph and mark these points. That's right. This will give us point 1, 8, 0. This one will give us 3 minus 3, 0, and the other point of got is 0 there. We've got 3 points there to plot. Then let's do that. I think I'll use the red color for that, so that you can differentiate the points. So we've got this point. We've got what? 1 comma 3. 1 comma 8. So close to 2 somewhere there. And we've got minus 3 comma 3 comma 3. Okay. So this one is an intercept on y and is an intercept on x. Is that all right? So with that. Then let's come up here and do our next step. Let our next step be, let's find the, let's say number this one 1. Let's differentiate the function. dy, oh sorry, let me say turning points. Turning points. Then for turning points, we need the first derivative. So let's get dy dx. X squared. X squared. Derivative of this. 6x squared plus 6x minus 12, which is the same thing as there's a 6 redundant there, we don't need it. Let's take it outside the brackets there to see whether we can factorize that. X squared plus x minus 2. Can that be factorized? Then how? Is x what's that? Minus 1 there plus 2 there. Now at the turning point, this derivative must be 0. That just says that to us x minus 1 multiplied by x plus 2 is equals to 0, because 6 will never equal to 0, isn't it? So those are the only two factors we can be equal to 0. Therefore, x equals to 1, x equals to minus 2. So now what we need to do, these are turning points. Now we need to calculate these turning points and find the other coordinate y. But where do we calculate the other turning point, the coordinate y? From the function itself. All together. So we come here now and say y coordinates for these points. Y coordinates of turning points, all right, the TP. So for x equals to 1, y equals 2. Give me that function is 2 brackets 1 cubed. Is that right? Plus 3 brackets 1 squared minus 12 brackets 1. I'm evaluating the function. Check that. I think, if I'm not mistaken, it should be 20 or so. What's the value? Minus 7. Also, I think I'm thinking about another value. Minus 7. So minus 7. That's it, 1. Okay. Now for x equals to minus 2. So guys, for this one, we've got a point we must plot, which is 1 minus 7. But let's get the two of them, then go to the graph and plot all of them. Mimicking the formula of the function again, 2 minus 2 cubed plus 3 minus 2 squared minus 12 minus 2. Please look at my beautiful use of brackets. Please use your brackets beautifully so that you communicate what you really intend to communicate. What's the value there? 20. Okay, so this is the value I was thinking about. 20. So I've got minus 2, 20. That's the value we must plot. Are we there? So let's go back to the graph. And for minus 2, there is minus 2. There is minus 2. There is 20. Do you agree? Okay. I think somewhere there, let's put an X for a point. That's the thing. Then the next one is what? It's minus 7, is it? Oh, minus 7. I think we'll need to reduce this view a bit. This is, let's get it 225. We have to reduce that. Was minus, you can't see minus 7 here. So for the next one, let's get this 1 and minus 7. This is counting in twos. 2, 5, 6, 7 must be there, isn't it? So let's get our red ink again there, and put minus 7 there. Then I think we're done with that line. So those are the points. Now we need to know now what's happening in this region, what's happening in that region. If a function is going to 10 there and have a 0 here, it has a 0 here. We must check what's happening here, what's happening there. Again here, there's a 10 here, there's a 0 here, 0 there. We must check what's happening there, what's happening there. Are we together? Okay, so let's go to our working page here. All right. Now, what do we need to do now? We need to look at the derivatives. Let's check the derivative before minus 2. Check the first derivative after minus 2. We just pick a point after minus 2. So where is the first derivative? There is the first derivative. 6x squared plus 6x minus 12. So let's write there. dy dx dy dx equals to 6x squared plus 6x minus 12. The turning point is at minus 2. Turning point is at x equals to minus 2. I think the best thing is, let's take the derivative, first derivative dx, that evaluated at x equals to, let's say, minus 5 over 2. What is that? Minus 2.5, isn't it? Okay, so it's on the left of that. Let's get that one. That is going to be 625 over 4 plus 6 multiplied by 5 over 2 minus 12. What do we get here? I think here we're going to get 3 times what? 3 times 5, which is 15. And it is 2. 15 negative 15. These two give us minus 15 minus 12. Minus what? Minus 27. Are we going to get something bigger than 27 here? Check that. Roughly this is 6 times 6, isn't it? This is actually more than 6. Altogether, 6 times 6 is 36. I'm doing a rough calculation here. Is that something? This is 6 comma something, but let me just round up to 6. 6 times 6, 36, which is less than what I actually want. So 36 minus 27 is clearly greater than 0. So it will be even more greater than 0. So which means the derivative there is greater than 0. So the function is f of x is increasing. Or you can say it's growing. I don't know. I think it's the same thing. The values of the function are growing. Then let's take the other one, which is, can say now dx, dy, dx evaluated at minus 3 halves, which will give us 6, 9 over 2. No, 9 over 4, sorry. 9 over 4, then plus the 6 times minus 3 over 2 minus 12. Let's check that calculation. What do you get there? This is minus 18 divided by 2 minus 7. Minus 7, comma 5. What do you get here? The whole answer is minus 7, comma 5. No. Then there's something wrong. Oh, minus 7, comma 5, you said. Okay, sorry. Okay, no, that's fine. So this means this is less than 0. The function must be decreasing. M less than 0. F of x is decreasing. Listen, guys, I hope you can observe, all of you, that our calculations here are communicated. We calculate, we make a kind of a statement there in words. It is difficult to do mathematics like this, just do calculations without interlacing with some like everyday language, communicate what you're saying. This tells me this tells me this. Then this is just going to justify what I'm going to do on or what I'm going to sketch on the graph. So if I go back to the graph here, I can just say from here to there, the function is going up. I can maybe do something like this. And at this side, the function is going down. I'm not saying draw this thing. I'm just doing it now so that we can share the thoughts we are supposed to be looking at now. This side function is going down, this side is going up, and so on. Then let's come to the other point now. Which other point is 1, is it? So we should check what's happening before 1 after this turning point, which is obvious, but just check it and confirm it mathematically. And then check what's happening after 1. So let's go back there. Take out derivative. Before 1, we can take half. dy dx evaluated at x equals to half. That's before 1. This was x, sorry. X equals to that. Then what we have there? We've got 6 multiplied by 1/4 plus 6 multiplied by 1 half minus 12. A quarter of 6 is less than 2, isn't it? A half of 6 is 3. Something less than 2 plus 3 is less than 5. 5 minus 12. This is less than 0. All together. Therefore, F is still decreasing there. As you can see, sometimes it's not necessary to work with exact values. I can see what, like you can see now, I'm just saying a quarter of 6 is less than 2, and half of this is 3, something less than 2 plus 3 less than 5. 5, that just to move faster. Is that right? But it must be clear that you are doing something like that, not just to fabricate things. dy dx evaluated at x equals to 3 halves. That's 1.5. That's after 1. Let's get that there. That will be 6 times 9 over 4 plus 6 times 3 over 2 minus 12. This is what? What is this? This is 3 times 3, which is 9, is it? And this is 6 times 9 is 54, isn't it? Divided by 4. What's your answer then? 54 divided by 4. 40 divided by 4 is 10. 10 plus 19. 10 plus 9 is 19 minus 12. This is greater than 0. I'm just doing an approximation again there, isn't it? Because you can't give me the exact number. So which means what? F of x is increasing. Who can remind me, what are we left with now? Sorry? Come again? Points of inflection. But also, the other thing we can do is to test our turning point, whether the turning point is really a maximum or minimum. But that change of positive to that indicates that it's a maximum. So it's increasing, suddenly it's decreasing. It's increasing by much. But what you can do, which I'm not going to do now because of time, is to evaluate the second derivative. The second derivative is the first derivative of the first derivative. Did you hear that? Sound like bit nonsense. Second derivative is the first derivative of the first derivative. In other words, you have got to take the first derivative of what already is a derivative. And then from there we know what is the third derivative. Is the first derivative of the second derivative. Is that right? There is the first derivative. The second derivative with the derivative of this, which will be 12x plus 6. Is that right? Applying power rule. 12x plus 6. Let's just evaluate this one just to make sure that we agree with our behavior of the tangents. Is that right? The turning point was at minus 2. Isn't it? So now we take this second derivative, evaluate it at minus 2, x minus equals to minus 2. Do you see, guys, how I write there? All together, do you see how I write it? If you don't want to write like this, make it more beautiful than this. All together? Okay. Then they would get 12 multiplied by minus 2 plus 6. This is minus 24 plus 6. Clearly, this is less than 0. Therefore, at x equals to minus 2, there is a local maximum. I'll just say local max. And this is a bit contradictory. The value of the function, the second derivative, is less than 0. No, being less than 0, it gives a feeling of being small, but its actual ways, the function is biggest in that locality altogether. So you must sense that contradiction when you look, with that feel of a false contradiction when you look at this thing. Less than 0 gives you maximum, more than 0 gives you local minimum. So let's omit that step now, because we said we were going to just check this one and go together. Now we are looking for point of inflection. Now, point of inflection will occur where the second derivative is equal to 0. So d2y dx d2, which is 12x plus 6. Sorry, we need to indicate that what now finding the points of inflection. There could be more than one, but we just write this. We expect it to be more than one, can be one or more, it's fine. So then we said second derivative must be 0, equal to 0. So let's set our second derivative to 12x plus what? 6 equals to 0. And this tells us that 12x is equal to minus 6. Therefore, this must occur at x equals to minus half. Now, that is the x coordinate of the point of inflection. Then, the y coordinate, who can tell me, where am I going to get it? No, where am I going to, what am I going to use to get the y coordinate? Come again? The original function. So we go to the original function, say y equals to, okay, sorry for that. Let's evaluate this function. It was 2 brackets minus half cubed, plus 3 brackets minus half squared minus 12 brackets minus half. Let's get that point and see what we get there. What are we getting, guys? 13 over 2, which is 6.5. Let's write it as 6,5. So we've got a point to plot as point of inflection here. Let's just write I there for inflection. For point of inflection, I'm just writing I there. Minus 2, let's say minus 0,5, like we wrote that one as 0,5. Let's just be decimal. And this other one is what? 6,5. I'm using a semicolon there because it looks like we've got a tendency of using commas for decimal points. So then let's get that one for to differentiate the others. Going to make a problem there. You're going to have a problem there. So then we go to our graph. We plot minus half. Minus half what? Minus half and 6,5, is it? Yeah, minus half is somewhere in the middle here. 6,5. This is 7. In the middle there. 6,5 must be somewhere there. Let's see whether we can get it. 6,5. Somewhere there. Halfway between 7 and what? So now we know from what we've discussed that the function is decreasing here up to that. There's a turning point there. The turning point is at minus what? 7. Then from minus 7 it's increasing. So now we now have got to hold our breath and start sketching this curve nicely. Listen guys, when I'm saying nicely, I mean nicely. It must look more or less that it was machine drawn. Drawing it like this, it's not nicely. All together, it's not nicely. You should really hold your breath and do something nice. Yeah. It's a rough sketch, but it mustn't be rough sketch. So let's go. Hold your breath with your graph there. You must be having your own axis, your own graph. I don't know what you've been doing so far. If you don't have it, then there's something wrong which was happening with you for the past minutes. Guys, if I can do it with an electronic pen, why can't you do it with a normal pen? There is the function. Y equals to 2x plus 2x cubed plus 3x squared minus 12x. It's a cubic function, 1, 2, 3 zeros. And everything else is shown. I mean, this is my best rough sketch under the conditions that I'm not using a normal pencil, which I learned to use in grade 1. I'm using an electronic pencil. I mean, guys, I think you accept my apology. All together. But from you, I expect better than what your teacher produced. Right. The signs are, our time is up. Thank you for listening. I think we'll still need one more example which involves curves having asymptotes. Goodbye for now.